Welcome back, everybody. So today we're going to talk about a very important property of real numbers, and that's the distributive property. So we actually already implicitly used the distributive property in our first problem series when we were actually calculating the sum of the first 10 even integers, 2 plus 4 plus 6, all the way up to 20. And what we did there was we factored out a common factor of 2. And so when we did that, we just assumed that you already knew everything there was to know about the distributive property, because that is a property of the distributive property. And so just in case that you don't, we're going to go ahead and cover the distributive property here. So this really, we're going to have several different types of videos that will show in this middle school problem solving series. So the first one is what we call our problems, where we'll take a common problem and we'll go ahead and develop the math in order to solve that problem. The second type is what we'll do here. We'll take a very important property of math, in this case the distributive property, and we'll develop that property, and we'll show how it leads to some common problems that you might encounter in your problem solving work. And the third type of video that we'll do is we'll actually do some advanced things. So when we have an advanced concept that is related to something that we've done, we'll go ahead and develop that advanced concept, and those kind of videos will just be optional. You can either not watch them at all or just watch them and get out what you can get out of it, and you'll eventually see all those more advanced topics later in your studies. So I'm back again here with Kyle. He's going to help me out again today. And so what we'll do is we really want to get at the distributive property, but we'll go ahead and kind of go through all of the properties of real numbers, so we kind of get the complete picture. So to do that, we'll go ahead and just talk about the real numbers. So we've got the real numbers, and those...
And if you don't know what that is, it's any number you can find on a real number line.
That's right, and we can distinguish those real numbers from the complex numbers, which is a more advanced topic that we'll probably cover in the high school problem solving series. So the real numbers are primarily the numbers that you're already familiar with.
Like 1, 2, 3, 4, got it.
Yep, so to get a better idea of what those real numbers are, we can break them up into other sets of numbers that kind of encompass those numbers. And so we'll start off by breaking the real numbers up into two sets that add together to give us back the full set of real numbers. And those are the rational numbers and the irrational numbers. So the rational numbers are basically any numbers that we can write as the ratios of two integers. So integers are basically numbers that if we wrote them in decimal form would have zeros after the decimal place. So we'll write them as a over b, where a and b are integers. So Kyle, give me an example of a rational number. So first of all, if we wrote them in decimal form, they would either have two types of decimals. One would be a terminating decimal, which means that it would stop at some point in time.
And there's another type that goes on forever.
Yeah, and that's called a repeating decimal. So give me an example of a terminating decimal.
1/4.
Or a terminating rational number. So we can write that as the ratio of two integers, which is 1 over 4, and that's going to equal what?
0.25.
All right, so that'll equal 0.25. So we can see that that terminates. So it's a 2 and a 5 after the decimal, and then it stops. There's nothing else. It's all zeros after that. So give me another one.
1/5.
1/5.
And that's even simpler. It's 0.2.
Okay, so that's 0.2. So now how about an example of a repeating rational number?
1/3.
All right, so let's try 1/3. What is that?
That is 0.3 going on forever.
Yeah,
and
so
if you want to write that out,
and it just
would
repeats
be
forever.
0.3 with as many 3's as you want, but you have a line over it.
Yeah, so for shortcuts, so we don't have to write all those 3's, we'll just write it as 0.3 with a line over, and that means that the 3 repeats forever. So how about give me one more?
1/7.
All right, so 1/7. So what is 1/7?
1/7 is 0.142857 going on forever. Now we can use the same thing we did with the line over that, as we can write it in here.
Yeah, so that means 1/7 is going to be 0.142857, 142857,
142857 on forever.
Gone forever. So the irrational numbers, so the property of the irrational numbers is they cannot be written as the ratio of two integers.
The
And
square root of 2 is with random numbers.
yeah, and so their property, if we wrote them as decimal numbers, would be that
They never stop.
they never stop and they don't repeat. So give me an example of your favorite irrational number.
Pi.
All right, so what is pi?
3.1415926535897.
Blah, 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 blah. All right, that's enough. So that'll just keep on going on forever, right? And it won't repeat. And so that's one property of irrational numbers.
I have a joke for you.
Oh, you got a joke. Awesome. Let's hear your joke.
What did one guy say to another guy about pi?
I don't know. What did he say?
Don't talk to that guy. He'll go on forever.
That's a good one. All right, I like that one, Kyle. Okay, so those are the irrational numbers. So we also got in the irrational numbers like square root of 2, square root of 3, constants like e. So all of those are irrational numbers. So they can't be written as the ratio of two integers. So let's go back to the rational numbers. So we can break the rational numbers up into two sets of numbers that when we add them together will give us back all of the rational numbers. So the first type is the non-integer fractions, positive and negative. So those are numbers that when we write them in decimal form, that they will have some number after the decimal point. It won't be all zeros. And then we can also have the integers, and those, if we wrote them in decimal form, have zeros after the decimal place.
It doesn't start with any number except 0 and always stays like that.
Yep, so a couple of examples of non-integer fractions would be 3/5, which is 0.6, minus 2/3,
Which is minus 0.66666 on forever.
repeating forever, or 1/8.
Which is 0.125.
Correct. All right, so all of those, if we write them in decimal form, after to the right of the decimal place, all have numbers that are not all zero. So the integers, on the other hand, have all zeros after the decimal place. So those are minus 2, minus 1, 0, 1, 2, going on forever in both directions. So remember that those are still rational numbers because we can write 2 as 2 over 1, and 2 and 1 are both integers. It just happens when we divide it out that we don't have any numbers to the right of the decimal point. So we can further break those integers up into the negative integers and the whole numbers. So the whole numbers are 0, 1, 2, 3, 4, 5, going on forever to the right. And then we can further break those whole numbers up into 0 and the counting numbers. So the counting numbers really are just the positive integers. So 1, 2, 3, 4, 5, going on forever. So those are our properties of real numbers, and those are all the different sets that we can break up the real numbers into. So hopefully you have a pretty good idea now of what the real numbers are. So now let's go to the properties of real numbers. So the first part with the properties of real numbers is that we have two operations that we can do on real numbers. So that's addition and multiplication. And then we have some properties that are satisfied. So the first four of those properties, they have a corresponding property for addition and for multiplication. So the first thing that we're going to assume is that we have three real numbers,
and A, B, and C, and let's just say that they can be any number you
Yep.
can pick.
So A, B, and C can be any real number whatsoever. And so the first property that we want to talk about is the commutative property.
And the commutative property states that if you're adding two numbers, you can flip-flop them.
Yep, so it says that it doesn't matter which one we add first. We can add A plus B,
Or we can add B plus A.
and that's exactly equivalent to B plus A. So that's the commutative property for addition. The commutative property for multiplication says that if we have two numbers, it doesn't matter the order in which we multiply them. So we can do A times B, and that's exactly equivalent to B times A. So the second property is the associative property. So now we have three real numbers, and the associative property says it doesn't matter which way we add, which two numbers that we add or multiply first. So we have that A plus parentheses B plus C is equal to parentheses A plus B plus C. And remember, the parentheses just changes the order of operations, and it tells you what you have to do first. So you always have to do what's in parentheses first. And so when we talk about multiplication, it's A times parentheses B times C. So we're going to do B times C first, and then multiply by A is exactly equivalent to multiplying A times B first, and then multiplying C. So then we have a couple of other properties. Property number 3 is the identity property. And so the identity property says, let's do for addition first, is if we want the identity property to be when we add it to any real number, we just get that real number back. So in this case, we all know that the identity for addition is 0. We take a plus 0, that's equal to 0 plus a, and that just gives us back a. For multiplication, is the identity for multiplication 0?
No, because that gives you 0.
Yeah, so that wouldn't give you a back. So the identity for multiplication
is actually 1.
That's right. It's a different number than it is for addition. So we know that 1 is the number that we want for multiplication because a times 1 is equal to 1 times a is equal to a. Any number times 1 just gives us that number back. So once we have our identity, we can define another property called the inverse property.
Which is what number plus that same number is 0.
Well, not that same number. What number, if I take a number a, what number
plus
the inverse will give you back the identity. So in the addition case, the identity is 0. So for addition, the number that we're looking for is the negation of a. So a plus the negation of a gives us back 0. For multiplication, we expect that it's not going to be the same thing, and it's not. The inverse for multiplication is the reciprocal. So if I take a and I multiply it by the reciprocal of a, I get back 1, which is the identity for multiplication. Okay, so those 4 properties are pretty important, and we're going to get to the property that we really want to study here, the distributive property. But before we do that, we want to look at some visual representations of why the commutative property and the associative property hold for addition and multiplication. Okay, so the first thing we want to look at is a visual representation of why the commutative law of addition holds. So let's say we're adding 2 numbers, a and b. So a is given by the purple circles, and that's going to equal 6. And b is going to be given by the orange circles, and that's going to be equal to 8. And so let's pretend that
the orange are orange gumballs and the purple are purple gumballs, since my dad loves gumballs.
That's right. So we want to add all of our gumballs together. So we want to know if it matters in which order that we add the gumballs. So let's find out. So we've got a number line here that says how many gumballs of each type that we have. Now let's just add these guys together. Now when they're added together,
we can see that it's on the same line, 14.
That's right. We can see that we get 14 when we add them together, but it doesn't matter whether I add my purple gumballs first, which is A, and then add my orange gumballs, which is B, which will give me 6 plus 8 is 14, or if I add my orange gumballs first, which is 8, plus my purple gumballs, which is 6, that also gives us 14, as we can see from the number line. So we can see that it isn't going to matter which ones we add first, we're still going to have the same amount of gumballs.
Exactly. Now let's look at the commutative law of multiplication.
Okay, so in this case, we want to multiply A and B together. So A will set equal to 6, and B will set equal to 8. So A will be given by the number of columns that we have, and B will be given by the number of rows that we have.
And we can think of these as like chocolate squares. How many chocolate squares are in the chocolate bar?
Yep, so when we do 6 times 8, we're going to have 6 plus 6 plus 6 plus 6, 8 times, right?
And I'll give you how many squares are in the chocolate bar. Or we can write it as 8 times 8 times 8 times 8, 6 times.
Correct. And what we can see from this is that this rectangle on the left is just, when it's 6 times 8, we just rotate that rectangle by 90 degrees, and then it becomes 8 times 6.
But when we rotate it by 90 degrees, we can see that it changes no such.
Yeah, so just by rotating our rectangle 90 degrees doesn't change the total number of squares that rectangle has. So therefore, we can see that 6 times 8 is going to be exactly equivalent to 8 times 6. It's just a rotation of that rectangle.
Now we're going on to the associative property.
Yep, so we'll look at the associative property of addition first. So say that we're going to add three numbers together, a, b, and c. So in this case, a equals 7, b equals 4, and c equals 2. So we're just going to color those numbers by which ones we're going to add together first. So if we're going to add the numbers together first, we'll color them the same color, blue. And then the ones that we'll add last, we'll color in red. So we can see here that we're going to add b plus c first, so that'll be in parentheses. So we have a plus parentheses b plus c. So that'll give us 7 plus parentheses 4 plus 2. And that's going to be 7 plus 6, which will be equal to 13 on the left. Now on the right, we're going to add a and b first. So we'll do 7 plus 4 in parentheses, which is 11, and then add 2, which is also equal to 13. So here we can see that it really doesn't matter how we color our rectangles, right? At the end of the day, we're still going to have exactly the same number of rectangles. Their color makes no difference whatsoever.
Nope.
So that demonstrates the associative property. So now let's look at the associative property of multiplication. So in this case, we want to count the total number of small black circles that we have. And we want to count them in two different ways. So the first way, we're going to count how many big squares that we have. And we can see that for
we have 6 big squares.
Yep, and for each big square,
we have 4 tiny dots.
Yep, so to get the number of big squares, we'll multiply our number of rows, which is 2, times our number of columns, which is 3. So we'll have 2 times 3 in parentheses, which is 6 big squares. And each square has 4 circles in it, so that'll be 24. The second way we want to count them is we want to count how many small circles we have in a row, and then multiply that by how many rows that we have. So how many big or small circles that we have in a row is given by how many columns we have, which is 3, times the number of small circles we have per square. So that's 3 times 4 is 12. So we can see that we have 12 small black circles per row, and we have 2 rows. So that's 12 times 2 is 24. Also gives us the same number. So we can see that because it doesn't matter how we count the number of small black circles that we have, whether we count the total number of big squares times how many small circles we have per square, or whether we count how many small circles we have per row and multiply it by how many rows that we get, we're still going to get exactly the same number of small black circles, right?
Exactly.
And so that's a demonstration of the associative property of multiplication. Okay, so now that we have a good understanding of the commutative properties and associative properties as they apply to addition and multiplication, now we'll move on to trying to understand the distributive property. So the distributive property doesn't have a form for addition and multiplication. It's actually what happens when we mix addition and multiplication in the same problem. So what it says is, if I have a series of terms that I'm adding together, and we'll put those in parentheses, and I want to multiply those all by a number a, so I've got a times parentheses b plus c, then that is going to equal a times b plus a times c. So that's why they call it the distributive property, because I'm actually going to distribute that a to each term of the sum in parentheses. So I'll have a times b plus a times c. And so the distributive property can also work in reverse. So if I'm working from the right side and I notice that I have a common factor in each term of my sum, then I can factor that common factor out to the front and just multiply that common factor times my sum in parentheses with the a divided out. So I'll have a times parentheses b plus c. So there's plenty of applications in math where you want to use distributive property going forward, which we call distribution, and the distributive property going backwards,
which is factoring,
which we call factoring.
I have a joke for you.
Really? Another joke? Awesome. Let's hear it.
Why did the president's distributive like to ignore all my votes?
I don't know. Why did he ignore all your votes? Sounds pretty rude.
Because he wanted to factor me out of the judging.
You must have, that one's so good, you must have made that one up yourself. Is that right?
Yep.
Oh, nice. Pretty good. So that's our distributive property. And so then we just want to do 2 additional things here before we look at a visual representation of the distributive property. We want to define 2 more operations. So we want to define the operation of subtraction, which will define in terms of addition. So we'll define a new operator called subtraction, which is given by this minus sign. So we'll define it as a minus b is equal to a plus the negation of b. So as an example, we all know that 7 minus 3 equals 4, so we better get 4 when we apply this definition of subtraction, right? So applying our definition of subtraction, 7 minus 3 is going to be given by 7 plus the negation of 3, and then we'll rewrite the 7 as 4 plus 3 plus the negation of 3.
And then the positive 3 and the negative 3 cancel out, so we're left with 4 plus 0, which is 4.
Yep, so the 3 plus the negation of 3, we know from our property number 4, inverse property for addition. I'm adding a number and it's negative. I know I'll get 0, so I have 4 plus 0 is equal to 4. So I indeed get 7 minus 3 is equal to 4, which is what I expect from doing it the traditional way. So we also want to define division in terms of multiplication. So we define a new operator, which we'll give by this slash sign, or it can be given by the division fraction bar. So a divided by b is equal to a times the reciprocal of b. Okay, so 6 divided by 3, we all know that's equal to 2. So let's better be equal to 2 when we apply this definition. So this is equal to 6 times the reciprocal of 3, which is 1/3. So we'll rewrite the 6 as 2 times 3 times 1/3.
And as we know from the inverse property of multiplication, we have 3 and it's reciprocal, so that equals 1. So we have 1 times 2, which is 2.
That's right. So a number times its reciprocal just gives us back 1. And we know from the identity property that any number times 1 just gives us that number back. So indeed we get 2. So these are using those in a couple of common examples when we can use our standard methods, but these definitions really come in handy when we're doing subtraction with negative numbers or division with different types of reciprocals or things like that. And one of the biggest applications for this definition of division is when we're actually dividing fractions. We don't actually have a standard way to divide fractions, so we define it in terms of this definition of division that we have here, and we actually call it, when we're using it for fractions, we call it KFC, or Kentucky Fried Chicken, so we can remember it. It means keep the first fraction the same.
And then flip the second fraction, or take the reciprocal of it, and then we change the division to the multiplication.
That's right. And so that is how we divide fractions, but it actually turns out that works for any numbers. We can do that same identity. And so one thing to note is that subtraction and division are not commutative, and they're not associative like addition and multiplication are. So you have to be very careful. And when you want to evaluate divisions and subtractions, when you want to move things around, it's better to convert them to additions and multiplications first.
And then you can.
And then it's commutative and associative, and then you can move them around. So keep that in mind when you're solving problems. Okay, so now we want to also get a visual understanding of the distributive property. Why does it work? So what we want to do here is we have 3 different numbers. A is given in red, B is in blue, and then C over here. So C is going to represent the number of rows in this rectangle. A is going to be the number of columns in the red part of the rectangle, and B is the number of columns in the blue rectangle. So what we want to do is we want to multiply C times parentheses A plus B. So what we're really doing is we're trying to calculate the number of squares that we have in this large rectangle. And similar to what we did before is we want to calculate how many squares we have in 2 different ways. So the first way that we want to do it is we want to multiply our total number of rows in our rectangle times our total number of columns in our rectangle. So that'll be given by C times parentheses A plus B, right? Because when we add A and B together, that gives us the total number of columns that we have. And that'll give us the total number of squares in the big rectangle. But we can also get the area by adding up the area of the red rectangle and adding that to the area of the blue rectangle, right? So the area of the red rectangle is given by C, its total number of rows, times A, its total number of columns, and then we'll add that to the area of the blue rectangle, which is given by C, its total number of rows, plus B, its number of columns. So in the case that we're showing here, where A is 8, B is 7, and C is 9, you can see that the area of the red rectangle is given by 9 times 8, and that's 72. The area of the blue rectangle is given by 9 times 7, which is 63. And when I add those together, I get 135. But we can also see that the area of the large rectangle is 9 times a plus b, which is 15. So 9 times 15 is also equal to 135. So that shows us that c times parentheses a plus b is equal to c times a plus c times b. And I think, so that is the distributive property. And it's just how we calculate these areas in different ways. Okay, so now that we've gone through all of the problems and we've talked a little bit about visually, we've seen with GeoGebra kind of why they work, so we have a pretty good feel for them. We want to look at some common problems that you might encounter using these properties. So we'll start off with some properties of the associative and commutative laws first. So we'll start off with addition. So let's look at problem number 1. We want to compute the sum 472 plus parentheses 292 plus 28 close parentheses. So how should we do this one, Kyle?
Well, we can use the associative and the commutative property, so we can take out the parentheses.
Okay, let's take out the parentheses. So the associative law says we can drop the parentheses.
And then the commutative law says that we can switch the 219 and the 28.
Okay, let's do that. And why would we want to do something like that?
Because we know that when we add 472 plus 28, it's going to be a power of 10.
Yep, it's going to end in a 0, and adding numbers that are powers of 10s are really easy, right?
So 472 plus 28, we know is 500. And then we have 500 plus 219, and that equals 719.
Exactly. So now we can take this problem and quickly do it in our heads, where if we tried to do it in the order that they gave us here, it would be a little bit more difficult.
So whenever possible, try to look for powers of 10 that can be multiplied or added.
Yep, so you want to be very familiar with how you get powers of 10 by adding. So 1 plus 9 is going to end in a 0, 2 plus 8 it will end in a 0, 3 plus 7 will end in a 0, 4 plus 6 will end in a 0, and 5 plus 5 will end in a 0. So we want to look for any of those combinations that will end in a 0 and make other numbers easy to add.
Exactly.
So let's continue with that. Let's go to number 2. So here we want to compute parentheses 2 plus 12 plus 22 plus 32, close parentheses, plus parentheses 8 plus 18 plus 28 plus 38, close parentheses.
And this sort of reminds me of Gauss's trick. So we can write this sum forward and this sum backwards, and then we'll have 2 plus 12 plus 22 plus 32, and under that we'll have 8 plus 18 plus 28 plus 38.
Okay, so we can drop the parentheses, right? And then we can add these in any order that we want. But let's go with your idea here.
And
right, this is 2 plus 12 plus 22 plus 32.
Then write this
Let's
sum
write
backwards.
this one backwards. So that means that'll be 38
plus 28
plus 28
plus
plus
18 plus
plus
8. And then we're going to add those together. We get 40, 40, 40, and 40.
So they all come out to be 40. That's nice.
And that's why it sort of reminds me of Gauss's trick. Then we have 40
It
4
definitely
times,
does.
and that is, of course, 160.
Exactly. So it takes some nice vision in order to be able to see that they can all come out to be 40. You could also have tried a 2 plus 8. That'll give you a power of 10, 12 plus 18, but that's not quite as easy because the numbers don't come out the same and you have to kind of keep track. But if you can see that you can add them together in such a way that you can always get the same number, then that's super nice, right? All right, so now let's look at some commutative associative properties for multiplication. So problem number 3 is compute 25 times 125 times 4 times 2.
Okay, so using the commutative property of multiplication, we can flip-flop 125 and 4, giving us 25 times 4 times 125 times 2.
Okay, and we'll actually even associate those guys.
And then 25 times 4 is 100, and 125 times 2 is 250. So then we get 25,000. And one trick we can do is we can drop the zeros. 1 times 25 is 25, then we can add the 3 zeros back on, equals 25,000.
Yep, and why can we do that is because we can write the 100 as 1 times 100
and we can write
times 250. So we can do the 250 times 1 first, right? So we can do 250 times 1. That's dropping the zeros of the 100. And then you'll multiply that by 100 at the end, but multiplying by 100 is just equivalent to adding 2 zeros to the end of your number. So whenever you're multiplying by a power of 10, you can drop those zeros because you can write the number as 1 times 100, or if you had 300, it would be 3 times 100, and then do the 250 times 3 first, then multiply by the 100, but that's just adding the zeros back on. So that's a nice little trick for multiplying powers of 10.
We have another problem, which is 25 times 17 times 4 times 20. Now we can use commutative logic again, writing it as 25 times 4 times 17 times 20.
Good, so we'll associate these guys and these guys. So now we'll have 100 times, we can use that same trick here, so 17 times 2 is 34, add the 0 back in, is 340, and we'll use it one more time.
And then we have 34 times 1, which is 34, then we add the 3 zeros, which is 34,000.
Boom. Right, so we can get these quickly in our heads just by simple rearrangements using our commutative and associative properties. So now we want to look at some examples of the distributive property. So for our first examples, we'll be actually using distribution, or we'll be using distributive property going in the forward direction. So the first examples, and it's one of my favorites, and it shows up, you can use it at a lot of different places when you're solving problems, is 2 by 1 multiplication. So in this case, we want to multiply a 2-digit number by a 1-digit number, but we want to do it quickly in our head. So our example is 43 times 7. So go ahead, Kyle.
So we have 43 times 7, which we can write 43 as 40 plus 3 in parentheses times 7. So then we can have 40 times 7 plus 3 times 7, and 40 times 7 is 280, and 7 times 3 is 21. And 280 plus 21 is 301.
Okay, so just like that. So instead of having to write it down in paper, very quickly to be able to do that in our head, with a little bit of practice, you can easily get all these 2 by 1 type multiplications extremely quickly in our heads. So problem number 2 is we've been talking a lot about multiplication being repetitive addition.
As we said in the last problem.
Yep, so now we want to actually show that's the case. The reason why we can show that's the case actually just comes from the distributive property.
Okay, so we have 20 times 8, and it's supposed to show that that's 20 plus 20 8 times, and so we can write 8 as parentheses 1 plus 1 plus 1 8 times. And
so
then
now
we can
we'll just apply the distributive.
Just apply the distributive, giving the 20 plus 20 plus 20 plus 20 8 times. And we know that anything times 1 using the identity property of multiplication, that's just itself.
Yep, so up to 20 times 1 using identity of multiplication are just 20s. So what do we end up with?
20.
We have 20 plus 20 plus
Which is what
20
we have here.
plus 20 8 times.
Which is what we have here.
And that we can add up quickly as 160. Right? So that indeed, coming out of the distributive property, shows that multiplication is repetitive addition. So now let's look at a couple of examples of the distributive property going in reverse, which, like we said before, is called factoring. So the first problem we want to solve is what is the value of 23 times 18 plus 40 times 18 plus 37 times 18?
Well, we have 3 18s in every single multiplication, so we can factor out the 18, giving us 18 times parentheses 23 plus 40 plus 37. And then we can use the commutative law inside the parentheses, so we can write 23 plus, maybe parentheses 23 plus 37 plus 40 in parentheses times 18.
So that's just 100. I won't write all that out. We'll just do that in our head now. So we know that we can do 23 plus 37 first, which is 60, and we'll add the 40 to that. Just gives me 100, so I have 100 times 18.
And we can drop the zeros. 18 times 1 is 18. Add the 2 zeros back, 1,800.
Then we just get 1,800. So that's much easier than trying to do each of those 3 multiplications individually and then trying to add up the results of those, right?
Now we have something that's sort of related to Gauss.
Yeah, so we did this problem in our first problem, but let's do it again to kind of refresh our memories, and it's going to become very important in the next problem that we're going to do, so pay close attention to this because it's going to be really important. So we want to calculate what's the sum of the first 10 even integers. So that's 2 plus 4 plus 6 all the way up to 20. So we notice that we can write...
we can factor out a common 2.
Yep, so we can write the 2 as 2 times 1. We can write the 4 as 2 times 2. We can write the 6 as 2 times 3.
And we can write the 20 as 2 times 10.
We can write the 20 as 2 times 10.
Then we can distribute out the 2.
We have a common factor of 2, each of those sums, so let's factor it out. So I've got 2 times, parentheses, now I'll write all those sums with the 2 divided out. So that'll give me the sum of the numbers from 1 to 10. And now I can use Gauss's trick here, so we know that it's n times n plus 1 over 2. But remember, if I ever forget that n times n plus 1 over 2, no big deal, because I know Gauss's trick. I'll just actually write it out.
That's it all the way to 10.
Then I'll do it backwards. I'll add them up. I'll see that they're all going to add up to be 11s. And I'm going to have that 11 10 times. So I'll have 11 times 10, but I got to divide it by 2 because I used 2 list, and that'll be 55. Okay, so I have 2 times 55, which is the sum of the numbers from 1 to 10, and that'll be 110. So the sum of the first 10 even integers is 110. Okay, so that's the same trick we used last time, and like I said, that'll be really, really important in the next problem that we do. And so now we'll go to just some general problems using the distributive law. So we looked at the first section was distributed going forward, now distributed going first, so now we'll just throw in some additional problems on distributive law. So the first one is we want to evaluate 999 times 275.
Okay, so we can write 99 as 1,000 minus 1.
Yeah, so we notice that 999 is super close to 1,000, and multiplying numbers by 1,000 is really a lot easier than multiplying numbers by 999. So multiplying numbers by 1,000 and multiplying numbers by 1 is super easy, so I'll rewrite the 999 as 1,000 minus 1
times 275. And now we can use factoring and
Nope, so this is distributive, so this is going forward, so I'll have 275,000, and that'll be minus 275. Okay, so let's just write that out. So 275,000 minus 275. So when you get good, you can actually do this in your head, but let's not do that in this case. Let's go ahead and just subtract it out. So that's 5, 2, 7, 4. So with a little bit of practice, like I said, you'll be able to get this in your head without too much trouble. So that's 274,725. So that's much easier, and essentially can all be done in our heads instead of trying to multiply all those 3-digit by 3-digit numbers out, which will take you a lot more time.
Because it'd be a pain in the butt to do a 3-digit multiplication, 999 times 275, without using our 1000 minus 1 trick.
Yep, so some of you skeptics out there might be saying, hold on a second. You showed that we have a distributive property for addition. You never said anything about having a distributive property for subtraction. And here you just wrote a subtraction and you just did the distributive law like you have a distributive law for subtraction. But I say, oh my friends, I do have a distributive law for subtraction. Let's write it out. Instead of writing our 1000 minus 1, let's convert it into an addition.
1000 plus negative 1 as we saw back.
Yep, let's write that as 1000 plus the negation of 1, which is negative 1, and that's times 275. And now I just have additions, so now I do have a distributive law.
Because back in the video, they said that any addition can be written, any subtraction can be written as plus the negative of that number.
Yep, so that'll be 275,000 plus negative 1 times 275.
And negative 1 times 275 is just minus 275.
Yeah, I'll just convert this.
Which is what we have.
I'll just use my definition of subtraction and just convert this back to subtraction now. So I can change the sign of addition to subtraction if I take the negation of my minus 1, and that'll just be plus 1, right? So 275,000. Now using my definition of subtraction, I can write that as a negative 275 times 1, which is just 275 times 1. So reconverting this back to addition, we do see that we can use distributive law with subtraction as well. And so problem number 2, our last problem for this particular series, is we have the number 222,222 is equal to the product of 37,037 times 6. So we want to know what is the product of 37,037 and 27.
Now we can write 27 as...
Alright, so here's the problem. So we have 37,037 times 27. We want to get this quickly. In our heads preferably if we can, or very little work.
27 is 6 plus 6 plus 6 plus 6 plus 3.
Right, so let's rewrite the 27 as 6 plus 6 plus 6 plus 6 plus 3.
Or 6 times 4 plus 3.
And now we can do distributive on this, right? So we got 37,037 times 6 plus 37,037 times 6 plus 37,037 times 6 plus 37,037 times 6 plus 37,037 times 3. And now I know that 37,037 times 6 is just 222,222 plus 222,222 plus 220,222 plus 222,222. Now I multiply it by 3, that's equivalent to multiplying by 6 and then dividing it all by 2. So that'll just be 222,222 divided by 2, which is just 111,111. So now when I add these up, it's very easy to do. You can see that I end up with 999,999. So this was an awful lot of material, but like I said, this associative, commutative, and distributive laws are super important, especially the distributive law. And so we'll see an example in our next problem just how important this distributive law is. So hopefully you are all feeling like experts now applying distributive law and factoring. And we'll see in our next problem how we can solve a really cool problem using what we know about Gauss's trick and what we know about the distributive law. So we'll see you next time.
Bye.